I must begin by clarifying what I mean when I speak of the universe being fundamentally unknowable, because this statement is easily misunderstood. I am not suggesting that we cannot learn anything about nature, that physics is futile, or that we should abandon the scientific enterprise in despair. Quite the contrary. I have devoted my entire life to understanding the physical world, and I believe we have made extraordinary progress, particularly in the 20th century with the development of quantum mechanics. What I mean is something more subtle and more profound, that there are fundamental limits to what we can know, limits imposed not by the crudeness of our instruments, or the limitations of human intellect, but by the very structure of nature itself. These limits are not deficiencies to be overcome by better technology or cleverer theories. They are intrinsic features of physical reality, and recognizing them is essential for understanding what quantum mechanics is really telling us about the universe. Let me start with a memory that shaped my thinking on these matters. When I was a young man studying physics at the University of Copenhagen, I was deeply influenced by the work of the philosopher Harold Hoffding, who lectured there and was a friend of my father's. Hoffding emphasized the limits of human knowledge and the role that our conceptual frameworks play in shaping what we can understand about the world. He argued that we do not have direct access to things as they are in themselves, but only to things as they appear to us through the lens of our concepts and experiences. This philosophical perspective stayed with me throughout my career, and it became particularly relevant when I began working on the quantum theory of the atom. The classical physics of Newton and Maxwell rested on certain assumptions about knowledge that seemed so obvious as to be beyond question. We assumed that physical objects have definite properties at all times, whether we observe them or not. We assumed that if we knew the positions and velocities of all particles at one moment, we could in principle calculate their positions and velocities at any future moment with perfect precision. We assumed that measurement is a passive process that simply reveals pre-existing properties without fundamentally altering the system being measured. And we assumed that we could, at least in principle, know everything there is to know about a physical system by making sufficiently careful observations. These assumptions seem to be confirmed by centuries of success. Newton's laws predicted planetary motions with astonishing accuracy. Maxwell's equations described electromagnetic phenomena beautifully. The mechanical worldview, where the universe was like a vast clockwork mechanism whose future could be calculated if only we knew its present state completely, seemed unassailable. Pierre-Simon Laplace famously imagined a demon, an intelligence that knew the positions and velocities of every particle in the universe, and could therefore predict all future states, and retrodict all past states. In this view, the universe might be complex, but it was knowable in principle. Ignorance was merely practical, never fundamental. Quantum mechanics shattered this comfortable picture, and it did so through a combination of experimental discoveries and theoretical necessities that could not be ignored. When I developed my model of the atom in 1913, I was trying to explain why atoms were stable despite the fact that classical electromagnetism predicted they should collapse instantly. My solution was to propose that electrons could only occupy certain discrete orbits, and that they made discontinuous quantum jumps between these orbits without passing through the space in between. This worked brilliantly for explaining atomic spectra, but it introduced an element of the unknowable right from the start. When would an electron make a quantum jump? I could calculate the probability of a transition, but I could not predict the exact moment it would occur. The timing was fundamentally random, not determined by any prior state or hidden variable that we simply failed to measure. This indeterminacy bothered many physicists, including Albert Einstein, but it was not just an artifact of my atomic model. As quantum mechanics developed through the 1920s, indeterminacy and fundamental unknowability became more and more central. Werner Heisenberg, working in my institute in Copenhagen, discovered his famous uncertainty principle in 1927. This principle states that you cannot simultaneously know both the position and the momentum of a particle with arbitrary precision. The more precisely you determine one quantity, the less precisely you can know the other. The product of the uncertainties must be greater than or equal to a specific minimum value determined by Planck's constant. Now, you might think this is just a practical limitation, that particles really do have definite positions and momenta, but our measurement techniques disturb them in ways we cannot fully control. Heisenberg himself initially described the uncertainty principle in terms of disturbance, imagining that measuring position with light necessarily disturbs momentum because photons carry momentum that gets transferred to the particle being observed. But this interpretation, while pedagogically useful, misses the deeper point. The uncertainty principle is not about measurement disturbance. It is about the fundamental nature of quantum states themselves. In quantum mechanics, position and momentum are represented by operators that do not commute with each other. This mathematical noncommutativity means that position and momentum cannot both have definite values at the same time. It is not that the particle has a definite position and momentum, but we cannot know both. Rather, the particle does not have definite values for both properties simultaneously. Before measurement, a particle is described by a wave function that encodes probabilities for different possible measurement outcomes. The wave function contains all the information there is about the particle, but this information is not sufficient to specify definite values for all observables at once. This is what I mean by fundamental unknowability. There are questions about quantum systems that have no answers, not because we lack information but because the questions themselves presuppose concepts that do not apply at the quantum level. What is the exact position and momentum of an electron right now? This question assumes the electron has definite position and momentum simultaneously, but quantum mechanics tells us this assumption is false. The question is meaningless, like asking what color a musical note is or what day of the week smells like lavender. We are trying to apply classical concepts to a domain where they simply do not fit. Let me illustrate this with the double-slit experiment, which Richard Feynman called the central mystery of quantum mechanics. When we send electrons one at a time through a barrier with two slits, each electron hits a screen on the other side at a specific location, behaving like a particle. But over time, the accumulated impacts build up an interference pattern, alternating bands of high and low probability, exactly as if each electron were a wave passing through both slits and interfering with itself. Now, if we place detectors at the slits to determine which slit each electron passes through, the interference pattern disappears. We get two simple bands, consistent with electrons behaving as particles that go through one slit or the other. What can we know about the electron's path through this apparatus? If we do not place detectors at the slits, we cannot know which slit the electron went through, and indeed the question has no answer because the electron did not go through one slit or the other. It was in a quantum superposition of going through both. But we do know that the electron will contribute to building up the interference pattern. If we do place detectors at the slits, we can know which slit the electron went through, but then we cannot know whether it would have contributed to an interference pattern, because the act of determining its path destroys the conditions necessary for interference. The two types of knowledge, which path the electron took and whether it interferes, are mutually exclusive. We can have one or the other, but not both. This mutual exclusivity is what I called complementarity. Complementarity is central to understanding the fundamental unknowability of the quantum world. Wave and particle properties are complementary. Position and momentum are complementary. Different spin components are complementary. In each case, we can design experiments to measure one property or the other, but the experimental arrangements necessary to measure one property are incompatible with those needed to measure the complementary property. Both properties are real aspects of the quantum system, both are necessary for a complete description, but they cannot be observed simultaneously. Nature herself enforces this limitation, not through crude mechanical disturbances but through the very structure of quantum states, and the way they interact with measuring apparatus. Einstein never accepted this picture. He believed that quantum mechanics, despite its practical success, must be incomplete. There must be some deeper level of description, he thought, some hidden variables that determine the actual properties of particles, with quantum mechanics merely reflecting our ignorance of these deeper realities. In 1935, he and his colleagues Boris Podolsky and Nathan Rosen published a famous paper presenting what they saw as a paradox in quantum mechanics. They showed that quantum mechanics predicted correlations between distant particles that seemed to require instantaneous influences across space, what Einstein mockingly called spooky action at a distance. Einstein thought this proved quantum mechanics was incomplete, that there must be local hidden variables determining the outcomes of measurements without any non-local influences. I spent many hours discussing these issues with Einstein, both in person and through correspondence. I understood his discomfort, truly I did. The idea that particles do not have definite properties until we measure them, that measurement plays this special creative role in bringing properties into existence, that nature enforces fundamental limits on what we can know simultaneously, all of this violated Einstein's deep intuitions about how reality should work. He wanted physics to describe the world as it is, independent of observation. He wanted determinism, locality, and completeness. But I could not agree with him. I argued that his objections were based on classical prejudices, assumptions about what physics should be like that needed to be abandoned in light of quantum mechanics. Physics, I maintained, is not about describing some hypothetical objective reality that exists independent of observation. Physics is about what we can actually measure, predict, and verify experimentally. If certain combinations of properties cannot be measured simultaneously, even in principle, then it is meaningless to insist that those properties exist simultaneously in some definite form behind the scenes. We must take seriously the operational meaning of physical concepts. Properties that cannot be measured, even in principle, are not physical properties at all but metaphysical speculation. Many years after Einstein and I debated these questions, John Bell developed a mathematical test that could distinguish between quantum mechanics and theories based on local hidden variables. Bell's theorem showed that any theory satisfying certain natural locality conditions would have to obey certain inequalities in the correlations between measurements on distant particles. Quantum mechanics predicts violations of these inequalities for certain entangled states. Experiments performed from the 1970s onward, with increasing sophistication and precision, have consistently confirmed the quantum mechanical predictions and violated Bell's inequalities. Einstein was wrong. There are no local hidden variables that could restore the classical picture while matching experimental results. The correlations predicted by quantum mechanics are real, and they cannot be explained by any theory where particles have definite properties independent of measurement, and where influences propagate only locally. What does this mean for the knowability of the universe? It means that certain questions about quantum systems simply do not have answers. What are the positions and momenta of all particles right now? No answer, because these properties do not exist simultaneously in definite form. What path did an electron take through a double-slit apparatus when we did not measure its path? No answer, because it did not take a definite path. What values would various spin components have before we measure them? No answer, because these values do not pre-exist measurement. The universe is fundamentally unknowable in the sense that there are aspects of it that cannot be known because they do not exist in definite form until brought into existence by interaction and measurement. But let me be clear about what this does not mean. It does not mean that anything goes, that reality is purely subjective, or that we create the world with our thoughts. Quantum mechanics makes precise predictions about measurement outcomes, and these predictions are constrained by objective laws. Different observers performing the same experiment will get consistent, if probabilistic, results. The wave function evolves according to the deterministic Schrödinger equation when no measurement occurs. There is an objective quantum reality, but it is not a reality of definite classical properties existing independently of observation. It is a reality of wave functions, superpositions, entanglements, probabilities, and the irreducible role of measurement in creating definite outcomes. Nor does fundamental unknowability mean that quantum mechanics is merely a practical tool without ontological implications. Some physicists have adopted an instrumentalist view, treating quantum mechanics as a black box for predicting experimental outcomes without worrying about what is really happening at the quantum level. I understand the appeal of this view, and for practical purposes it works fine. But I believe we can and should take quantum mechanics seriously as telling us something profound about the nature of reality, even if that reality is stranger than classical intuitions would suggest. The fact that we cannot visualize quantum processes in classical terms does not mean they are unreal or merely mathematical. It means that reality at the quantum level is genuinely different from reality at the macroscopic level, and we must adjust our philosophical frameworks accordingly. The fundamental unknowability I am describing is not a confession of ignorance or defeat. It is a positive insight, a recognition of how nature actually works at its most basic level. It tells us that the universe has a quantum structure that enforces limits on what can be known, not through practical obstacles but through the very nature of quantum states and observables. Position and momentum cannot both be known precisely because they do not both exist precisely. Wave and particle properties cannot be observed simultaneously because observing one requires an experimental arrangement that precludes observing the other. The path of an unobserved particle cannot be known because it does not take a definite path. This has deep philosophical implications. The ancient Greek atomists imagined that if we could just see small enough, we would find tiny indivisible particles with definite shapes and motions, and all phenomena could be explained in terms of the arrangements and movements of these atoms. This reductionist, mechanistic vision has been extraordinarily influential in science. But quantum mechanics tells us that this vision is fundamentally wrong. When we probe to the smallest scales, we do not find little billiard balls with definite properties. We find wave functions, superpositions, uncertainties, and complementarities. The microscopic world is not just the macroscopic world made smaller. It is qualitatively different, operating according to principles that have no classical analog. This also has implications for the relationship between knowledge and reality. In classical physics, we could maintain a clear separation between the knower and the known, between the subject observing and the object observed. We imagine that nature exists out there with definite properties. And our job as scientists is to discover these properties through careful measurement, always striving to minimize our disturbance of the system being observed. But quantum mechanics collapses this separation. Measurement is not a passive revelation of pre-existing properties but an interaction that brings properties into definite existence. The measuring apparatus, which must be described classically in order for us to communicate results, cannot be separated from the quantum system being measured. They form an integrated whole during the measurement process. This is not mysticism or idealism. I am not saying that consciousness creates reality, or that the universe depends on observers for its existence. The key is interaction, not awareness. When a quantum system interacts with a macroscopic apparatus in a way that creates an irreversible record, a definite outcome manifests. This happens whether or not any human is present to witness it. The universe existed for billions of years before there were conscious observers, and quantum processes occurred throughout that time, with outcomes determined by natural interactions. But those outcomes were not predetermined by some complete set of properties that particles possessed independent of interaction. They emerged through the quantum process of measurement, understood in the broad sense as any interaction that correlates a quantum system with a macroscopic record. I developed the concept of complementarity to help make sense of all this. Complementarity recognizes that quantum systems have multiple aspects that are all necessary for a complete description but that are mutually exclusive in observation. We need both wave and particle descriptions, both position and momentum, both conjugate spin components, but we can never observe both members of a complementary pair simultaneously. The experimental arrangement that reveals one aspect necessarily precludes the arrangement needed to reveal the complementary aspect. This is not a limitation of technology but a fundamental feature of quantum reality. Some people have criticized complementarity as being vague or merely a philosophical overlay on the mathematical formalism of quantum mechanics. But I see it differently. Complementarity is an attempt to articulate clearly the epistemological lessons of quantum mechanics, to explain why certain questions cannot be answered and why certain combinations of knowledge are impossible. It helps us avoid the trap of assuming that quantum systems are just like classical objects but smaller, that they must have all the properties classical objects have. Complementarity teaches us to think more carefully about what we mean by physical properties and physical knowledge. The fundamental unknowability of the universe also has implications for the old philosophical question of determinism versus free will. Classical physics was deterministic, at least in principle. If Laplace's demon knew the complete state of the universe at one moment, it could calculate all future states. This seemed to leave no room for genuine freedom or spontaneity. Everything was predetermined by the laws of physics and initial conditions. But quantum mechanics introduces genuine randomness into nature. When an excited atom decays, emitting a photon and dropping to a lower energy state, quantum mechanics can tell us the probability per unit time of this transition, but it cannot tell us the exact moment it will occur. The timing is genuinely random, not determined by any prior state or hidden variable, as far as we can tell. Does this quantum randomness create space for free will? I am not sure, and I was always cautious about drawing too direct a connection between quantum physics and questions of human freedom. Human decisions involve astronomically complex neural processes, and while individual quantum events may be random, the behavior of large systems generally averages out to be statistically predictable even if not deterministically certain. But what I can say is that quantum mechanics has definitively shown that nature is not the clockwork mechanism that Laplace envisioned. There is genuine openness in the universe, genuine unpredictability at the fundamental level, and this at least removes the strict determinism that seemed to eliminate all possibility of spontaneity or novelty. The universe is fundamentally unknowable not because we are ignorant or limited, but because nature herself is structured in a way that enforces limits on what can be known. These limits are mathematically precise, experimentally verified, and conceptually coherent once we abandon classical prejudices. Heisenberg's uncertainty principle gives us exact quantitative bounds on what combinations of properties can be simultaneously known. Complementarity gives us a framework for understanding why these limitations exist and what they mean for our conception of reality. The violation of Bell's inequalities proves that no local hidden variable theory can restore classical knowability while matching experimental results. I have spent decades thinking about these questions, discussing them with colleagues, defending the quantum view against those who wanted to restore classical intuitions, and trying to articulate clearly what quantum mechanics is telling us about the nature of knowledge and reality. It has been a difficult journey, intellectually and emotionally. There is something deeply unsettling about recognizing that the universe resists our attempts to know it completely, that nature herself places limits on what can be known, that we must give up the dream of a complete, visualizable, deterministic picture of physical reality. But I have also come to see beauty in this limitation. The universe is not a closed book that we could in principle read completely if only we were clever enough. It is fundamentally open, irreducibly probabilistic, always containing an element of mystery. Every measurement creates new knowledge but simultaneously limits what else can be known due to complementarity and uncertainty. We can never know everything about a quantum system, but we can know enough to make precise predictions about what will happen in specific experimental situations, and this knowledge has proven extraordinarily powerful and useful. Quantum mechanics has been tested more thoroughly than any theory in the history of science, and it has never failed. Every exotic prediction, from tunneling through barriers to the creation of particle-antiparticle pairs from vacuum, from the quantization of magnetic flux in superconductors to the precise energy levels of atoms, has been confirmed. This is not the mark of a theory that misunderstands reality or fails to capture something important. This is the mark of truth, of having discovered genuine features of nature, even if those features are stranger than we expected. The universe is fundamentally unknowable in specific, precise ways defined by quantum mechanics. We cannot know position and momentum simultaneously beyond the limits set by the uncertainty principle. We cannot know which path a particle took and whether it interfered. We cannot know all components of spin simultaneously. We cannot predict the exact moment of a quantum transition, only its probability. These are not gaps in our knowledge that future discoveries will fill. They are fundamental features of quantum reality that we must accept if we are to understand nature as it truly is. And yet, paradoxically, recognizing what we cannot know is itself a form of deep knowledge. We know the precise limits of knowability. We know why certain questions cannot be answered. We know the mathematical structure of quantum mechanics that enforces these limits. We know how to make extraordinarily accurate predictions within the boundaries of what can be known. This is not ignorance. This is profound understanding, hard won through experiment and theory, of the quantum structure of reality. When I say the universe is fundamentally unknowable, I am celebrating one of the greatest discoveries in the history of human thought, that nature has a structure, revealed by quantum mechanics, that is both more subtle and more strange than we imagined, that enforces precise limits on knowledge, and that these limits are not defects but features. Not obstacles but insights into the deepest nature of physical reality itself.